This video is focusing on topic number 1 of your electricity unit. So if you could take out your notes in electricity, we're going to go through the first topic and highlight one of the key things, which is talking about charge, and explain how charge is developed and how charge is defined. So in your notes, this is the area that we're going to focus on, is electric charge. And again, we're going to go through and define the key points underneath that electric charge. On your own, you will need to review static electricity, the structure of matter, fundamental laws of electric charge, charging an object, charging by friction, what is an electroscope, and explain the differences between charging by contact and by induction. This is all grade 9 information. You will have to go back and review pages 422 to 432 just to go over those topics, take some notes. Again, you don't need to memorize that information, but just to review it, understand it, and be familiar with the terms and the concepts that are involved with each one of those as we go through the unit. But for now, this video is going to focus on is the idea of fields and point charges and so on, and what that is and how that relates to current. So we're going to go back to the idea of an ebonite rod and a pith ball, right? Two things that you would have used in grade 9. Remember, the ebonite rod you rubbed with fur and you created a charge through that electrostatic series. So we've made this ebonite rod negative. And then the pith ball you would have charged by contact, and you've made that now negative. Now, when you create a charge on the ebonite rod, and also on the pith ball, but we'll kind of focus just on the ebonite rod. The ebonite rod not only is negative on the material itself, but around the rod, we're going to draw this red area, which is going to be a field. And this would be an electric field. And that electric field, is the same charge as the object itself. So we would fill this in with a bunch of negatives. Now, in grade 9, you would have put that ebonite rod close to, but not touching the pith ball, and then the pith ball would have moved away from it because like charges repel. No direct contact was made when this occurred, and there's no direct contact because the electric field, which is negative, influenced the pith ball and its electric field and created a repulsive force, and that's what forced the pith ball to move away from it. Now, this electric field, again, it's something that you can't see. You can't really outline it, and you can't really go in and actually touch this electric field. But you can see the result of it. And a lot of the things that we're going to talk about in terms of electric field is looking at the results that we see in physics and then trying to put a model that explains what is happening. Again, we have not really ever seen the electric field. We just know it's there. We know it influences. We can use it in different applications. However, the diagrams that we use from it, the models we use, again, are built from the result of different experiments. So that's really, in general, what an electric field is. It's a field that's surrounding any charged object, whether it's negative or positive, and it is the same charge as the actual charged object. And so you can influence things at a distance, even though there's no direct contact. Now, we can use diagrams to show the electric field. So we can use a positive, so that's representing the charge, and when we have a positive, we draw arrows moving away from the charge, showing the direction of the field. And again, we know this is the direction of the field, again, by experiments that have been done looking at a positive charge, looking how a positive charge behaves in different environments. And so from that, we've built a model suggesting that the positive charge, the the field that's created from that is an outwards direction. The negative works the opposite, and so we would have arrows pointing inwards or towards the charge, and that would be a standard or conventional drawing for a positive and negative charge indicating the direction of the fields. Again, it's a model. It's just a model suggesting that there is a field around the charge and that these are suggested directions of the charge themselves. Now we can use the drawing, so we could use, for example, the positive, and we can draw lines moving out from there. And there are a couple things that you can get from the lines. First of all, if I draw a number of lines coming out, and we look at the differences in densities in the line, or the line orientations, from the center or from the charge outwards, we can see that the densities change. So if I look at, say, the middle, or not the middle, sorry, right at the charge itself. So if I look right here, around this section, this blue section here, if I was to count up the area, so take the, say, the circumference of that circle that I just drew, so this circle here, and then the number of lines that are intersecting that circle or passing through that circle, we would say the number of lines per surface area would be greater than if I moved outwards to the outside. This is very similar to the concentric wave patterns that you would see in sound, right? As the sound waves move away, there's less intensity or less power per unit area for sound. It's the same thing with electric field. As I move outwards, as I go out this direction, the intensity of the strength per unit area decreases as I move away from the charge. And that's why as you move further away from the charge, the force of attraction and repulsion is reduced. So as you move away from the charge, attraction, I'm just going to use A, or repulsive force decreases. And again, it's dealing with the concentration of the strength. So again, because of that really concentric wave pattern, or that concentric pattern, or that circular pattern that we see in this diagram, because it's spreading further out, again, your intensity level is less per unit area, and that's what's causing it to decrease. And that's why you would see the same thing happen in a magnet. That would be a familiar application of this. Those are called magnetic field lines, and they work the same way as electric field lines. As you move magnets further apart, like the north and south ends further apart, there's less of a force of attraction. If you move them closer together, they suddenly come, there's an attraction which will pull them close together, and that's because you're getting into the area where the concentration level is much, much higher. Same thing happens with repulsive forces. So definitely in field diagrams, arrows show the direction, so whether it's positive or negative, the density of the arrows, right? So really the location you are from the center or the charge also indicates the strength. The other thing that, the other aspect that field lines can also show, or electric field diagrams can show, is the number of lines coming from the charge itself. So again, I'm going to use the positive as the example. So I could compare, say, 4 lines coming out from the positive charge, the first one, so this would be charge number 1, and then I could then increase the number of lines, so I can add 8 to the second one here. What this diagram shows is that the second charge is stronger than the first charge by the number of arrows, and then the last one, then I could just continue to add lines. So I'd have 8, and then I'm going to add an extra line in between each of the existing lines. And as we move from the left to right, we have an increase in strength in the diagrams because of the actual number of arrows. So field diagrams show really 3 basic things. They show the direction of the strength, which means that it's either going positive or negative. It shows the density of the lines, which means that the closer you are to the charge, the stronger the repulsive or attractive force there is. And then you can also show the overall strength, which is this last diagram, of the charge itself. So the more you charge an object, the stronger that repulsive or attractive force is. And that is also showed by the number of lines, which means that as you're going again from the left to the right here, you're getting a stronger charge.